Is up, everyone? Hope you are doing well today. Today I'm really excited to make this video, but Signals and Systems is a course I did in my electrical engineering degree. I took a very great professor doing a lot of fantastic work in his research right now. His name's Dr. Narayanan. I also had the opportunity to do a little bit of research with him and another professor working with salmonella, which was super cool. Um, but one thing I learned about in Dr. Narayanan's Signals and Systems course junior year was the Basel problem, or the Basel problem. Not really sure how you pronounce that, but it was this problem that they had for the series, the summation, and basically they wanted to find if this had a closed form. And a very famous mathematician who changed, a lot of the world as we know it, Euler, he found that the exact sum was pi squared over 6 in 1735. And so this is all pulled from Wikipedia, as you can see in the caption. But if you just go into Google and you look up the Basel problem, you can go to the Basel problem Wikipedia page, and you can see this is just where I pulled right here. And so what's really interesting is that, so it says that his arguments were based on manipulations that were not justified at the time, although later proving correct. So, he discovered it in 1735, but 6 years later it was formally accepted as a proof. And so one thing that Euler was very well known for is kind of his contributions to signal analysis and signal processing. There's something very fundamental in any digital device called a Fourier transform, and it's named after Joseph Fourier. Joseph Fourier was also French, based on his last name. Very, very interesting dude. I think in a lot of, I'm not entirely sure, but a lot of his history stems from him trying to apply differential equations and like applications of things. He wasn't just a pure math theoricist. But as you can see, this is some pretty complex math. So we're going to look at this kind of Wikipedia here, but they start out with the Taylor series expansion of the sine function. So this is the Taylor series expansion. Then they divide through by x. And then there's something called the Weierstrass factorization theorem. The left-hand side is a product of linear factors given by its roots for finite polynomials. Euler said this was a heuristic for expanding an infinite degree polynomial in terms of its roots, but not always true for general p of x, I guess a general polynomial. And so what he was able to do is factor this Taylor series expansion into this form after dividing through by x, of course. And then it looks like formally multiply out the product, something by Newton's identity. And so, it's an equivalency here. And so he gets that, I can't follow all of this proof, and definitely not right now. But we essentially get this right here, this result, some sort of induction-based proof that this side is equal to this side, and then we want to isolate the sum term because that's what we're trying to solve for. So the thing is this series is known. That's why it can be reduced to this minus 1 over 6, because this is just sine x over x evaluated at, I think, pi, it looks like, or sorry, I can't follow all the details right here. I'm so sorry, Dr. Narayanan. Please don't be ashamed of me if you're watching this. Yes, it's a complex math problem, It's like you look at this and you see, wow, that's a lot of math. Sweet. So, they get to this result, right? Pi squared over 6. You would never think 1 over n squared, interestingly goes to pi squared over 6. What's really neat is this thing is called a pi. I learned about it. I think it's called a p sum. P series or something. Convergence. And what's really neat is if you look at this term, if this was 1 over n, the series would converge. So P series convergence is something that you learn about in Cal 2. It's basically the idea of, let's see if we can look it up on Wikipedia. P series, P series test. Looks like there's maybe some math page we can go to. All right, so a sub n equals da 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 from n equals 1 to infinity. You know, what's really interesting is this series will, or this summation will only converge if p is greater than 1. And, you know, that's just kind of counterintuitive in some regards. But that was kind of all I wanted to do, look at the wiki. And then I also wanted to just kind of bring up this little document I'm drafting for let's seeing like how we can engage with AI and see if AI has the capability of debunking this very interesting problem. But so I got Bard AI on the left here. Bard AI is Google's large language model tool. And so we're going to look at we're going to ask, can we have some context on the Basel problem, both historical and technical details, please? Then what I'm going to do is I'm going to actually grab this so that y'all can take a look at what I did in the document and get this all smaller. I'm going to underline this. I'm going to say, maybe I'll say prompt. So this is a lot less formal than my other videos. But this is our prompt. Maybe we will actually, so we'll do underline, then bold. So interestingly, yeah, so we are given all of this context for the background, you know, a lot more than we even probably got from Wikipedia. We got, interestingly, we got a lot of solution kind of code and stuff. It looks like this is all marked down, so you can't really read it intuitively. But I guess you would have to maybe grab the markdown. Right, so it has relevance to number theory. St. Petersburg Academy of Sciences. You know, this right here, I believe, is actually yeah, so this is a link to the Wikipedia where it pulls this number on the left here. Right, so it's the sum of the inverse squares of all natural numbers. It gives some background I didn't know about. It was apparently first posed by this guy named Pietro Mengoli in 1650, so about 40 years before Euler. But this was kind of a huge thing that brought Euler fame, apparently. He was 28 when he solved this problem. Isn't that wild? He was young. He was extremely young. Cool. Well, I'm going to copy this and then maybe try to see if we can't get that in a more clean form. So as you can see, it's kind of clean, but I mean, you can't really tell what's going on here. So I'm going to come up here, I'm going to make this all a bit smaller. Or maybe put this on a new page. I don't know if this can even go any smaller, but I don't really like that it's all. I don't really know if I should even put this in a document. It's kind of unreadable. Yeah, we're actually not gonna. We'll keep we'll keep all of this except for this because this isn't readable mathematics. So what I'm gonna do here now is I'm gonna look at let's see if we can get that in a cleaner form. So what I'm gonna do is I'm actually gonna provide feedback. That's one of the beautiful thing about these systems is they they have memory, so they can go off of your previous input and output. They save state. So let's look at this. What can you please? I am unable to read the math formatting in the browser of the text that was returned in your response. Sorry, my typing's bad. Can we please regenerate with kind of readable format? Okay, so it just shows us the solution. This is more readable, comma, but can we look at the proof? Because we, ultimately we know solutions, but if you can't understand the proof to get there. Okay, so it looks like it uses some idea of zeta functions kind of further down, I think from the Wikipedia page. Not entirely satisfied with Bard's return of this, but they evaluate the zeta function at 2. Honestly couldn't tell you off the top of my head. Okay, looks like some more. The Riemann zeta, right? So here's the Riemann zeta. You evaluate the Riemann zeta function at s equals 2, and then you get the reciprocal. So that's what I think when people confuse this tool about, is this tool is nothing more than a glorified Google or Wikipedia. Like it just, in its essential quintessential form, that's all it really is. Sorry, that's my friend. But that's all I had today. Have a great rest of your day, and goodbye.